Hello, Integrated Math 1. Welcome to Module 2, Topic 1, Lesson 2. We're doing the first half of the lesson today, and of course, you'll do the other half of the lesson later in the week. So we're going to start with Activity 2.1, since we've already done our warm-up and we've already done our Getting Started activity, and just reminded ourselves about how to find slope and reminded ourselves about how we know whether or not a function is linear, right? Based on a scenario or a table or an equation or a graph. We just have so many different ways of representing our linear functions now. So let's talk about interpreting our linear functions. So each table of values in that Getting Started activity, the previous activity we did, had consecutive input values, right? So 1, 2, 3, 4, or 6, 7, 8, 9 in our x's. So tables in that format allow you to use differences to determine whether the representation is linear, right? You can just find the difference in the y values. But often input values are in intervals other than 1. They're not necessarily, or they're not even in order, right? Sometimes input values are in a random order. So you don't have 1, 2, 3, 4. You have 3, 6, 4, 8 for your inputs. It can be all kinds of things. So to determine whether or not these tables represent linear functions, you need to make sure that your slope or average rate of change is constant between all given points. You can't just check one set, you have to check all of them. And you have to use the full-on slope or average rate of change, where you subtract your y values on top and you subtract your x values on the bottom. That you can't just use the y values. You need to make sure that you're doing your y values on top and the difference of your x values in the denominator, because it's no longer just like bing, 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 bing in order anymore. So we got to be a little more thorough and a little more careful. So what you're gonna do, I've got some new tables for you. I would like you to determine whether each of these tables, you have several of them here on page M2-25, you got a couple of tables. I would like you to determine whether each table represents a linear function. And if it does represent a linear function, write the function. So that means you're going to need to use your slope formula, right? You remember the slope, subtract your y's in the numerator, subtract your x's in the denominator. You're going to need to use that 1, 2, 3 times, all right? So use it for, grab 2 points, these two, and these two. Do the slope formula each time for all of them. And you know how this goes. If the slope is constant, you keep getting the same slope or the same average rate of change, you know it's a linear function. If you're getting different numbers, that's when you're like, no, that's not a linear function. All right. If it is a linear function, write the function for me as well. Go ahead and hit pause to work these out, and then hit play when you're ready to check your work. Okay, so here's what I did. So these guys, I started off with these guys right here. I'm going to use my pen here. So I started off with these guys over here, and I was like, all right, I want to find the slope of these two. So I subtracted my y values on top. So 4.75 minus 5.5, and then subtracted my x values on the bottom, 1 minus a negative 2. And then I had to do some cleaning up. 4.75 minus 5.5, I grabbed a calculator, and I got negative 0.75. The double negative here becomes a positive. So instead of 1 minus a negative 2, that actually becomes 1 plus 2, which gives me 3. And then if I divide those, I get negative 0.25. Yay. And then I'm going to do the same thing again for these guys. So 4 minus 4.75 over 4 minus 1. And then I worked that out, and again, got negative 0.75 over 3, and again, got negative 0.25. So this is a good sign so far, but you never know, this last one could screw us up. So I did it one more time using these 2 points. So 3.25 minus 4 on top, 7 minus 4 on the bottom. And I again got negative 0.75 over 3, which of course, again, simplifies down to negative 0.25. So this is good. So this means, okay, this bad boy is a linear function. I'm like, hey, it's a linear function. So that's good. So I know it's a linear function, which is the first thing we needed to decide. But I also have to write the function. And of all the weird things, I'm going to use my arithmetic explicit sequence to help me do that because I know what the first term is. Look, term number 1 is 4.75. There it is. So since term number 1 is 4.75, I'm going to use that. I can see that my common difference is negative 0.25. So I'm going to use that, only instead of n, a sub n, I'm going to use f of x because it is a function. And instead of n, I'm going to use x. But here's my first term number 1. There it is, term number 1. And my common difference. And then I'm just going to clean it up. So I went ahead and I distributed my negative 0.25. So I have negative 0.25x. And then negative 0.25 times negative 1 gives me a positive 0.25. I'm going to move my x term up the front. And then, of course, 4.75 plus 0.25 gives me 5. And look at that. I just wrote a function. Yeah. Feel so talented. I feel so smart. So that's a weird little trick that I use my arithmetic explicit sequence to help me write my function. Weird, but it works. I know it's a linear function, so it's all good. Then we had table B. And so again, I was like, all right, let's find the slope between these guys. Oh, so, whoa, my pen went weird. Stop that, little pen. What is happening? What is happening? My pen, it went out of control. Here, that's better. So I'm going to find the slope between these 2 points. So 13 minus 5 over 2 minus 0. So I did that, and 13 minus 5 is 8, 2 minus 0 is 2, so I got a 4. Great. I'm going to find the slope again between these guys, so 21 minus 13 over 4 minus 2. So 21 minus 13 is 8, 4 minus 2 is 2. I still have a 4. That's a good sign. But don't forget, we got to check this last set, so I'm going to check this last set. So 29 minus 21 over 8 minus 4. 29 minus 21 is 8, but 8 minus 4 is 4, and 8 divided by 4 is 2. So close. So I do not have a constant rate of change. I don't have a constant slope. It changed at some point. And this is why you've got to check all of your points, because this is not a linear function. So much sadness. But I mean, I guess I'm not writing a function for it then, since it's not a linear function. So I guess that's a little less work. It's not a bad thing, I suppose. So yeah, it didn't match, not a linear function. Cool. So let's actually start analyzing some situations of linear functions and all this good stuff. So Dylan sells pretzels at festivals on weekends. The table shown is a record of past sales. So what does this table tell you about his sales? I might look at slopes a little bit and see if that tells you something about his sales, about his number of pretzels sold and the amount of money he has earned. See if you can play with the slopes a little bit and see if it tells you something about his sales. Go ahead and hit pause and then hit play when you're ready to check your work. So slope. I didn't do the slopes for all of them. I just picked these first 2 points here to do the slope. So I did 105 minus 37.5 over 42 minus 15. So I just did that. And the Y values were in dollars, right? So $105 minus $37.5 gave me $67.5. 42 pretzels, because our X was in pretzels. So 42 pretzels minus 15 pretzels gives me 27 pretzels. So when he sold, so for 27 pretzels, he made $67.5, or $67.50. So when I divided that, I realized that means that my average rate of change here was 2.5. That means that Dylan was earning $2.50 per pretzel. So here you thought you were just finding the slope, but what's interesting is we know that the slope was in dollars per pretzel, right? These are the dollars on top, my pretzels on the bottom. So this tells me that Dylan was earning $2.50 per pretzel. So this average rate of change, the slope thing, actually does give you some interesting information about Dylan's sales, that he was getting $2.50 per pretzel. So how much money would Dylan earn if he sold 75 pretzels? Now that you have this information, go ahead and hit pause to work it out and hit play when you're ready to check your work. Okay, so if he was earning $2.50 for selling one pretzel, because it's $2.50 per pretzel. So if he was earning $2.50 for selling one pretzel, for each pretzel, that means that if he sold 75, well, you would need to do $2.50 times 75. And this is why I have a calculator. And it turns out that if Dylan sells 75, if Dylan sells 75 pretzels, he earns $187.50. All right. Not a bad day's work, I suppose. Let's go to another situation. This one's going to get a little more complicated, a little more funky. You ever been to the county fair? You ever been to the county fair? You know that you have to pay to get in, right? And then you have to pay more for tickets to go on rides, unless you're a single rider, in which case they don't let you go on any of the rides. But that's okay. I'm strong and independent, and it's not a big deal that they would not let me go on the Ferris wheel. It's fine. So Delaney and her friends recently went to the community fair. They had to pay an entrance fee and then purchase one ticket for each ride. Dakota is going to the fair tomorrow and wants to know the cost of each ride ticket, right? She's got a budget. So Delaney and her friends helped Dakota by writing down how much money they spent and the number of tickets they purchased. So here we have this lovely table that, now keep in mind, this is how much money they spent, and it includes the entrance fee. And then, of course, how many ride tickets they bought as well. So believe it or not, this table does tell you about the cost to go to the fair, and it also can give you the information about how much it was to ride the rides. Again, I would suggest picking two of these points. I don't care which two, pick two, and find the slope and see if you can use it to find out how much it costs to go to the fair and how much it costs to ride the rides. Yeah, go ahead and hit pause, find that slope, see what you can do with it and what it can tell you, and then hit play when you're ready to check your work. So I did the slope. I wanted to keep it simple, so I just picked these first 2 points because it was just, they were there, they were easy to use. So I used my slope formula and I was like, okay, 9 minus 7.5 on top, 4 minus 2 on the bottom. 9 minus 7.5 gives me 1.5, 4 minus 2 is 2, and 1.5 divided by 2 is 0.75. Now, what is this that we just found? That's an important question. Well, if you look, remember last time, dollars per pretzel. So if we look, my Y is in dollars divided by my number of tickets. So this is going to be dollars per ticket. So it looks like it's 75 cents per ticket. So that actually is good to know. So the ride tickets cost 75 cents each, 0.75 per ticket. So that's great for the rides, for the ride tickets, but the question also asks, how much did it cost to get into the fair? So to do this, I had to get a little more creative, and I looked at this first point and I was like, okay, well, she bought 2 tickets. So 2 times 0.75, but the total she spent was $7.50. So if I do 7.5 minus 2 times 0.75, because she bought 2 tickets, and if I subtract that out of her total cost, that should tell me how much it costs to get into the fair. So negative 2.75 times 0.75 is negative 1.5. And then, of course, she spent $7.50. So $7.50 minus $1.50 gives me $6. Looks like our entrance fee is $6. So of all the weird things, we actually did have everything we needed here. It was easy to find the cost per ticket And we just had to get a little creative and push ourselves a little further to figure out what that entrance fee was going to be. But we did find it. So $6 to get in and then 75 cents per ticket. Good to know. Good to know. So here's the deal now. We're going to mess with you a little more. So if Dakota has $20 to spend, parents gave her $20 to go spend at the fair, how many ride tickets can she buy? And remember, part of that $20 has to include what it costs her to get into the fair. So go ahead and hit pause, play with this, see what you can do with this, and then hit play when you're ready to check your work. All right, so this is going to be weird and you may not have done this, but I just wrote a little function because I was like, okay, well, it's 75 cents per ticket plus another $6 just to get in. So I wrote it like this, 0.75 times X plus 6. So 75 cents per ticket, but you got to add on that $6 just to get into the fair. And she has $20 to spend. So I want to know when this is going to equal $20. Well, first of all, I'm going to subtract out the cost of the entrance fee. So minus 6, 20 minus 6, of course, gives me $14 left. And now I need to figure out how many tickets. So I'm just going to divide both sides by 0.75. So if I divide both of these sides by 0.75, I get the X is about 18.66666 is going forever and ever and ever and ever. Maybe you want to round it with a 7. It's up to you. But can Dakota buy 18.7 tickets? You either buy a ticket or you don't buy a ticket, right? You don't buy like a piece of a ticket. That's not how it works. And $20 is her limit. She can't go over $20. So it looks like even though I got X equals 18.6, it doesn't make sense to buy a piece of a ticket. You either buy one or you don't. So I'm going to have to round down on this one and say, look, Dakota can buy 18 ride tickets because in this particular situation, that's what she can do. Let's do a new situation. 18 ride tickets, man, I would be so sick by the end of that fair. Maybe she should go on fewer rides and use some of that money to like buy cotton candy or something. But that's just my opinion. The local pet store has a fish tank on display at the community fair. Darren is responsible for draining the tank at the end of the fair. The pet store manager provides him with this information from when they drained the tank at the end of the fair last year. Okay, so last year, this is after a quarter of an hour, they still had 169 gallons in the tank. After half an hour, they still had 163 gallons in the tank, and on. You get the idea. So here's the deal. We want to know how many gallons of water the fish tank can hold. And again, I'm going to give you a hint. Start by finding the average rate of change. Start by finding that slope. It really does help. And then see if you can use it to find your answer. So go ahead and hit pause to work this out, play with it, see what you can do. Again, use that slope, it'll be helpful. And then hit play when you're ready to check your work. Okay, so I started off with my average rate of change, started off with my slope, and I just used the first 2 points because it was just the easiest. So I did 163 over minus 169 over 1/2 minus 1/4. And yes, this got a little messy, but if you wanted to turn these into decimals, that would have been fine as well. It's up to you. But I did 163 minus 169, which gave me a -6. 1/2 minus 1/4 leaves me with 1/4. And I don't like dividing with fractions. I multiply by the reciprocal instead. So instead of -6 divided by 1/4, it's actually -6 times 4. And that gives me a -24. If you had done 0.5 minus 0.25, turned it into decimals, it would have gotten you the same answer. Now notice it's -24 gallons per hour. And that makes sense because he's draining the tank, right? So the amount of gallons in the tank should be getting lower as we go. And that does appear to be what's happening on our table. So it makes sense that I'm getting a negative rate of change. That seems fair. The only thing is that tells me how many gallons per hour, but that doesn't actually tell me how many gallons are in the tank. So I had to get, again, a little creative here. I had to think about this, and I thought, well, after a quarter of an hour, there were 169 gallons. So I thought, okay, well, I'm going to do 169 gallons minus however much had already been drained. So I have a negative 24, and that's per hour, but it was only a quarter of an hour. So if I do negative 24 times a quarter, that gives me a 6, and the double negative makes that a positive. And I get 169 plus 6, right? And that equals 175. So it looks like the fish tank can hold about 175 gallons of water. That's a lot of water. It's a big tank, probably has a lot of fish in it. That's only fair. That's only fair. All right, let's take this a step further then. Now that we know how many gallons the fish tank can hold, here's my next question. When will the tank be empty? If it's 175 gallons and drain it, I can drain it at a rate of 24 gallons per hour. How long will it take to drain my tank? Go ahead and hit pause, see what you can do with this, and then hit play when you're ready to check your work. Okay, so 175 gallons, and each hour I'm pulling out 24 gallons. So I did 175 divided by 24. That's what I did. And if you're having a hard time seeing why that works, basically what I've got here is I've got 175 gallons. I'm gonna write it this way, 175 gallons divided by 24 gallons per hour. And what happens is that the gallons cancel out and you just have hours left. So that's why this works. I love using my units to make sure that things work and things cancel that are supposed to cancel, and I'm left with what I'm left with. So when I did that, I got 7.29 hours. It's about how long it'll take for the tank to empty. If you would like to be a little more precise, instead of saying 7.29 hours, then I got really precise. I grabbed a calculator and I was like, so it will be 7 hours, 17 minutes, and 30 seconds. Let's be honest. Darren just probably let that thing go for like 7.5 hours. He didn't time it down to the second. I'm feeling pretty confident he did not do that. All right then. Let's go to activity 2.2. Now that I've had fun messing with you, let's talk about our linear functions instead of tables. Let's talk about our linear functions in terms of graphs and what we can do with them and the cool stuff that they tell us. So Marilyn sells silk-screened t-shirts for her mom at local festivals. After each festival, she returns whatever money she earns to her mom. The graph shown represents her potential earnings based on the number of t-shirts she sells. So here we have this lovely graph that tells us how much she could potentially earn given how many t-shirts she sells. And you can see my x-axis is the number of t-shirts. My y-axis is her potential earnings in dollars. So I'd like you to take a moment to just analyze and interpret the graph. Just list as many facts as you can about this scenario based on what you see in the graph, and just describe how they relate to the scenario. So what does this graph tell you about Marilyn selling t-shirts? Go ahead and hit pause, jot down some of your thoughts, and hit play, and we'll have a little discussion about it. You'll notice there were some hints off to the side, like what does the slope mean in this situation? What does the x-intercept tell you about the situation? The y-intercept, the range, the domain. What do these things that you know about graphs tell you about the situation? So I had a few thoughts on this. I noticed that my x and y-intercept were both sitting here at 0. And that does tell me something. That tells me that Maryland starts with $0 for 0 t-shirts sold. So looking at that x-intercept, y-intercept, which happen to be the same spot, was helpful. It tells me she makes no money if she doesn't sell any t-shirts. Fair enough. But I mean, you can go further. Like I was like, well, if I come over here to 4 and I go up, 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 and I see it hits right there, that tells me that if she sells 4 t-shirts, she earns $60. You may have picked a different spot, all that good stuff. But I can also use that to help me find the slope, right? If I rise 60 with a run of 4, 60 divided by 4 tells me that she's making $15 per t-shirt. So this slope, this average rate of change, actually tells me what Marilyn is making per t-shirt. So this graph is kind of cool because it actually gives me a lot of information. 4 t-shirts make $60. That means $15 per t-shirt. No t-shirts means no bucks. So there is some good information to be found here. I think we kind of already did this. Interpret the meaning of the origin. So we're just saying that when x is 0, y is 0, and I'm going to write that in function notation, f of 0 equals 0. And we already said this means if no t-shirts are sold, Marilyn does not earn any money. And her mama probably ain't going to be happy with her at that point. Be careful, Marilyn. I got some questions about Marilyn and her mom, but you know what? Their relationship is personal. It's their business. It's fine. I would like you to write a function for this. Write a function for this. And instead of calling it f of x, we're going to call our function e of t. E for the earnings, t for the number of t-shirts she sells. So can you write a function? And if you need to, remember our function notation was f of x equals ax plus b. Now, of course, we're going to be using e's and t's instead. Or you may remember it as y equals mx plus b, that kind of stuff. But again, we're going to use e's and t's instead of x's and y's. So go ahead and write down a lovely function for Marilyn's potential earnings given the number of t-shirts she sells. Hit pause to write it down. Hit play when you're ready to check your work. So I noticed that her slope was 15. We noticed that earlier, right? That we were like, oh, $15 per t-shirt. So it's 15t. I'll go with that. I also noticed though that her y-intercept was 0. So 15t plus 0, except I don't really need the plus 0. So I just wrote that her function, instead of writing it, because I was like, okay, so y equals 15 was my slope plus 0. But we're going to use e of t instead of x. We're going to use t instead of x. And I don't need to put a plus 0 on there. I don't need to put plus 0. So it looks like our function here is e of t equals 15t. So what do these things represent in terms of the graph? What's t? What's e of t? What does it mean in terms of the function? What are those things? And what does it mean in terms of our graph? Go ahead and hit pause. Just jot down your thoughts on what those things are. Hit play when you're ready to check your work. So for my function, I was like, okay, well, t is the number of t-shirts, and e of t is the amount of earnings, or the dollar earnings, the potential earnings for selling t-shirts. As far as a graph goes, because that is a point, right? Like I could pick a point on the graph and my t would be my x-axis and my e of t would be my y-axis. So I just said that it represents the number of t-shirts sold and the money earned for the amount of for that amount of shirts. You get the idea. So what I'd like you to do now that we have a function for e of t in addition to our graph, now that we know that e is our potential earnings and t is our number of t-shirts, and also you remember how on last week when we did the whole find f of 1 and you plugged in a 1 and that told you what f of 1 is, or find f of 4 and we plugged in a 4, that's all it means. I would like you to do question number 5. You have a couple of these. I want you to evaluate each of these and interpret the meaning in terms of the equation, the graph, the scenario, all that good stuff. So go ahead and hit pause to work this out and give a little explanation, and then hit play when you're ready to check your work. Okay, so we said that E of t equals 15t. So everywhere I see a t, I'm going to plug in a 2. Hey, so E of 2 is actually 15 times 2, which is $30. So this means that it would give me a point of 230 on my graph, and it means that if 2 t-shirts are sold, Marilyn earns $30. Yay! So this is where the point would be on the graph, and of course, you sell 2 t-shirts, you earn 30 bucks. All right then. For part B, I have E of 5. So fine, that just means I'm going to plug in a 5. So instead of 15t, I have 15 times 5, which gives me 75. So that means my point is at 575 on my graph. And it means that if 5 t-shirts are sold, Marilyn earns $75. Yay! I have a little bit more. This gets a little more complicated. I have E of 2.75. So I did 15 times 2.75, and that gives me 41.25. This is a problem because while I could graph that point on a graph, 2.75, 41.25, this doesn't make sense. Remember that T stands for the number of t-shirts. You either sell a t-shirt or you don't sell a t-shirt. You don't sell 2.75 t-shirts. You don't sell a piece of a t-shirt. Most people don't like it when you do that. They want the rest. They want the whole shirt, oddly enough. So this situation, while I could actually get an answer for it, it actually does not make sense. And I can even put a point on the graph, on the line, but it doesn't make sense in our scenario because Marilyn can't sell 2.75 t-shirts. That's weird. So Marilyn has a goal at the festival. Marilyn has a goal to earn $100 at the festival. So let's consider how to determine the number of t-shirts she needs to sell to meet her goal. She wants to make $100, so how would she figure out how many t-shirts she has to sell? So I have it worked out here. So to determine the number of t-shirt sales it takes to earn $100 using our function, E of t equals 15t, I'm going to substitute 100 for E of t. So instead of E of t equals 15t, I'm going to say 100 equals 15t and then solve it. So I divide both sides by 15, which gets my t alone. And then 100 divided by 15 gives me 6.67. So t equals 6.67. Now, considering this worked example, can you interpret for me the meaning of our answer, t equals 6.67? Go ahead and hit pause, jot down your thoughts on this, and then hit play when you're ready to continue your work. So I know that T stands for the number of t-shirts. So to earn $100, 6.67 t-shirts must be sold. But again, we're not selling pieces of t-shirts. You're either going to sell 6 t-shirts or you're going to sell 7 t-shirts. There's no option in between. So, of course, if she sells 6 t-shirts, she won't make it to $100. She'll be a little below. So this says I need to round up. So therefore, to earn at least $100, Marilyn must sell 7 t-shirts because we sell the whole shirt, not just a sleeve. That's weird. Considering this worked example, let me ask another question. Why can you substitute 100 for E of t? Why was that okay to do? Go ahead and hit pause, jot down your thoughts on that, and then hit play when you're ready to keep the discussion going. So remember that E of t is our potential earnings in dollars. Do you remember that? So E of t represents dollars earned based upon T, the number of t-shirts sold. So that means if $100 is what we're earning, then that's where it's going to go. It's going to replace EFT because EFT is representing that dollars that we earned. And that's why it's okay to substitute that in there. Now here's a cool trick. So you can totally see how we can solve this with an equation, no big deal. But I've got an extra special bonus for you. Did you know that you can also use the graph to determine the number of t-shirts that Marilyn needs to sell to earn $100? Yeah, it's a cool trick. So here we have her lovely graph, her linear function, E of t equals 15t, yay. But remember how we substituted in that 100 and we were like 100 equals 15t. It turns out that what you can do is first graph, you can graph each side of the equation and then look at where they intersect. So we substituted in that 100, right? To determine the number of t-shirt sales it takes to earn $100, you need to determine the intersection of our two lines represented by the equation 100 equals 15t. So I graphed this side, y equals 100, and you can totally use Desmos to help you do that. Woo! And then I graphed the other side, y equals 15x. I did put an x back in there because Desmos likes x's a little better than t's. And I graphed that guy, and then I could totally use Desmos and be like, boom! Oops, sorry, I didn't mean to do that. That is where they intersect. And you can see I got 6.67, 100. So in terms of the graph, again, you can see we got 6.7 t-shirts to earn $100. So she needs, and just like we said before, it means she needs to sell 7 t-shirts. This is great and all. If you have Desmos, you could totally do this without Desmos as well. It just starts to get a little funkier, but it's okay. So it's kind of a cool trick that you can go ahead and set up your equation and instead of solving it, just graph each side and see where they intersect. Also a great way to find a solution. The graph will do it for you. Now you can see that there's downsides to these. So our last little question here, I'd like you to consider A, the equation, and B, the graphical way that we solved it. What are the limitations to using each one to answer questions about the number of t-shirts sold or the amount of money earned? So we got the same answer both ways, but why were there problems with doing it by solving the equation, part A, and why might it be difficult to do it by graphing it, part B? Go ahead and hit pause, jot down your thoughts on these for A and B, and then hit play when you're ready to check your work. So for the equation was great. I like solving equations. The equations solve really well. That was super awesome. But I don't know about you, but the issue I encountered is that sometimes an equation provides an answer that does not make sense in the context of our situation. And the answer must be rounded up or down to answer the actual question. In fact, we encountered that a few times, didn't we? We encountered that with buying ride tickets. We now encounter that with selling t-shirts at the fair, that depending on the situation, I may have to round up or round down because the decimals just didn't make sense, right? You buy a ticket or you don't buy a ticket. You sell a t-shirt or you don't sell a t-shirt. That the whole like 0.75 or 0.67 just doesn't make sense anymore. So you do have to kind of watch out for that. And of course, the issue with the graph is that while it was really awesome, that I like graphs because I can see the answer, like boom, that's where they intersect, that's where the answer is. I love that. But of course, the problem with that is that sometimes it's difficult to read an exact answer from a graph. If you're using Desmos, that's awesome. But if you're not using Desmos, if you're just looking at it on the paper and you're looking at that point and you're trying to figure out what your numbers are, it can be a little difficult to get an exact answer off of your graph. So graphs are great, equations are great, but they both have limitations. And so you have to kind of use your judgment on when it's better to use one or the other. It's a thing. It's a thing. As always, guys, I hope you found this helpful and I hope you found this useful. If you got questions or concerns, feel free to email me or come see me during office hours, and I'll see you soon. Bye.